And if you have any questions, doubts, you can ask. Actually, you should ask more questions. Particularly MTech students are not asking any questions. What is the reason? Actually, I also included the axial deformation, so it's basically, yeah. Timosenko means it is only basically bending degrees of freedom, so V and theta. But I included axial displacement also. So you can always, if there is only transverse load, you can drop out U naught, and then you will have basically V and theta as the variable. So maybe I'll discuss when I start. Penalty method might be for implementing boundary conditions. Yeah, so essentially whatever boundary conditions are there, one is that I taught you direct substitution. So there is another approach called penalty approach. So whatever constraints are there, that you take all the terms on one side, say left hand side, it's a square multiplied by a large number which is known as penalty parameter, and then you add that also to the integral functional, and in the minimization process you get some extra terms which enforces the boundary conditions. So maybe I'll discuss that sometimes, but you can read from the books. It's a simple concept. So are there any other questions? So there were two questions, so I think let me elaborate a little bit. So one was on the, I started with, so in the last class, Timosenko beam element. So actually, I have, what I have done is Timosenko beam theory based frame element, in fact. So the question asked was, in the books, typically Timosenko beam element means you only have basically bending degrees of freedom, that is V and theta. So you always, what we did, we considered an element which is subjected to transverse force as well as axial force. Of course, these are distributed forces, there can be concentrated forces and moments. So this we said it's as Qy, and then we had this Qx, this distributed force along x direction. And here is your element x axis, and this is y axis. So now see, if there are no axial forces, that is no distributed axial force, no concentrated axial force, in that case U naught would be 0. So then the variables you will have is only V and theta z. So for a two noded element you will have only 4 elemental degrees of freedom, so your matrices would be 4 by 4 and so on, so that you can always deduce. So from the Timosenko the frame Timosenko theory based frame element, you can always get to the Timosenko beam element without axial displacement degrees of freedom. So that was one question. So you can always, so when I talked about the degrees of freedom of the element, what I said is that at least we should have 2 nodes within the element, and then the primary variables I said U naught 1, then U naught 2, V1, V2, and theta Z1, theta Z2. So these are the degrees of freedom. Theta Z1, of course, if you want, you can write as theta 1, theta 2. So see, if there are no axial forces, this you can take 0. this you can take 0. So you will have a Timoshenko beam element only for modeling bending under transverse loading without the this axial displacement u naught. So every phi node u naught by dx or u naught wherever it is coming, that will go to 0. So that is you can always deduce from that. So I included this axial degree of freedom also. So it's more like a Timoshenko beam theory based frame element what we actually discussed. From that you can always deduce this. The second question was implementation of boundary conditions. So see, when you are what I taught, so one was the direct substitution, so that is what I taught you. Another is you can also use penalty function, penalty approach, not function. So in this what you do, say you have set of equations. So maybe since the question was asked, let me quickly explain you this. Although I think you should be, some of the things you should read. So this should be kind of a self-study. So let us say that we have a system of equation. Let me take a rod problem and subject it to certain constraints. So let us say that here I have got u equal to 0. You are discretizing this into two elements. So this is element 1, this is element 2, and this is the global node number 1. This is 2, this is 3. This is a rod problem, and this is subjected to say distributed axial force, which is q naught. Now if you want to solve this problem, and let us say each element length is L, so EA by L you can take common, and here what then you will get is 1, minus 1, 0, the assembly 2 and minus 1, 0, minus 1 and 1 into u1, u2, u3 is equal to right hand side. I am directly writing this kind of examples we have done earlier. So here the load vector would be QL by 2, QL and QL by 2 after assembly, and plus the internal forces which are minus Q11 and Q21 minus Q12 and Q22. These are your internal forces. So now when you want to actually implement the boundary conditions, so the boundary condition in this case are one boundary condition is that u1 is equal to 0, and what you actually do is implement these boundary conditions. Of course this you will still go through the same process. So that is q21 minus q12 equal to 0 in this case, because there is no concentrated force at node number 2, so this is 0. Now this is directly that means you're putting this term equal to 0, and similarly at the end there is no concentrated force, so q22 will also be 0. So these of course you still actually use the direct substitution, that put this equal to 0, this equal to 0. Now implementing this, what you can do is you can also use a penalty function approach. Penalty function approach meaning is that you in case of penalty approach, what you do, whatever integral functional we have got for actually whole system, so in that you add a penalty term. So the penalty term is, we take a large number, let me say that number as kp, the single scalar number, so kp by 2, and let me generalize this little bit more. Rather than saying that u1 equal to 0, I'll just modify this and say that this is some u naught. So rather than a 0, of course as a specific case it can always be 0. So let us say that this is actually equal to u naught. And now we want to implement this boundary condition that u1 is equal to u naught in the set of equations. So what you would actually be doing is in the direct substitution approach, what you are doing, putting u1 equal to u naught, then considering second and third equation. So whatever you get EA minus EA by L into u naught in the second equation, that you will take to the right hand side. Third equation, of course this term is 0, so it won't contribute, but depending on the problem you will take care of that and then solve for u2 and u3. But here what you do, rather than eliminating any of these equations, you actually consider all the three equations, but now this condition has to be incorporated. So if I try to write a corresponding energy like term, so I can say that Kp by 2 into U1 minus U0 whole square. So this we call as penalty energy term. So see, what it means is that when we are trying to solve the problem, if U0 is U1 is not equal to U0, so a small difference multiplied by with a large number Kp. Kp is a large number, and basically a positive large number. So if this number is a large, a small difference will give rise to a large value of this penalty term. So when you choose a large value of Kp, it will always try to minimize the difference between U1 and U0. So that is, U1 would be tending to U0 when Kp is a large number. Kp is tending to infinity, U1 would tend to U0. So this the energy like term, and when you take, so I'll just I'll only say that this is IP, the energy like term coming from the your boundary condition. So this is IP. Now if you look at delta of IP, that is variation in this, that would be Kp and twice of U1 minus U0, so that 2 and this half gets cancelled. So you have U0, U1 minus U0, this is what you get. This is a known quantity, so into delta of U1, basically this is going to get added with your remaining equations, whatever equations are existing. So now if you look at in this, so if you look at this particular system, you have delta U1, which is again you are saying it's an unknown, so it's arbitrary. The other two terms are, one you have Kp into U1 and minus Kp into U0. This is what you get as your delta of IP. That is, your delta of IP is this. So rather than saying that it implies, let me put here delta of IP going to this. And this is arbitrary. So in your equations, this is what would be added. Now this is an unknown, so you will modify the equations. So if you add this term, if it was added into your energy functional, this term will also be getting added. Since this is going with delta U1 in the global system, this will go to the first row. And so now in this, in terms of unknown, this is coming in the first column. So this side, what will happen is you already have this EA by L here, and in the equations now you are also going to add this. So here you have already 1, and since I have taken this EA by L common out, so let me write here Kp into L upon EA. So this will be actually added here in the equations, because this is with delta U1s in the first row, this is U1s in the first column. So this term is added because I have EA by L common, so I have multiplied here L upon EA. So when you take it inside, it gets basically Kp. So EA by L plus Kp, that is what you will be getting here finally. And of course here it's minus 1, that remains as it is 0, because there is no U2 and U3 term in this, and the other terms remain same, 2, and this is minus 1, 0, minus 1 and 1, and then you have here U1, U2, U3, and the right side what you actually get is this. So this is here QL by 2, and here also you have got QL by 2. You also have actually this minus Q1, 1. So this is what you have already. That is because this is equal to 0, this is equal to 0. So this plus this is what you will get. Plus this term you will take Kp into U0, which is a known quantity on the right hand side. But this is because was coming from delta U1, so it will go to the first row. So plus here due to penalty we will add this Kp into U0 here, 0 and 0. Then what you do, now you solve these equations simultaneously. Only thing is you will just ignore actually this term, or you can say that you would actually be ignoring this term whatever you have, because this number is going to be actually very large, Kp into U0. So when you now solve this equation as it is, all the three equations simultaneously, for a large value of Kp you will get your U1 equal to 0, and U2 and U3 is whatever is the solution. So rest of the solution you can look at. So then what you do is essentially in the penalty approach, whatever boundary conditions are there, so you are thinking of constructing a energy like term like this, and then you take its variation, and then through the variation you see what would be the contribution because of this penalty term into the left hand side, that is stiffness matrix, and into the load vector on the right hand side. So the columns are going to be decided on the basis of this variables, whether it is u1 or u2 or u3, and the rows are decided on the basis of this. So that will obviously will depend on which variable is prescribed. Suppose u3 is also prescribed, u3 is equal to some u naught dash. So you will have one more term here, and then that will contribute to penalty stiffness term here, and on the load vector side it will contribute actually here if u3 is also prescribed and you want to specify through penalty term approach. So this is in brief, and you can actually read about this from Belungundu and Chandru Patla. So that deals with the implementation of boundary conditions through penalty approach. And this is similar to if some of you would have done optimization. So when you have a constraint optimization problem, so the constraints can either be incorporated in an optimization problem through direct substitution or through penalty function approach. Of course, there is another one known as Lagrange multiplier approach that can also be used here, but the penalty function approach to implement the boundary condition is same as what we do in optimization. So see here also ultimately if you see what we are doing is the solution of the governing equations of these problems are actually the equivalent to minimization of your total potential energy functional. So essentially you have a total potential energy functional for these problems, and you are minimizing that subject to the boundary conditions. So those boundary conditions can be implemented as a direct substitution or penalty or even Lagrange multiplier approach. So the more details you read from the book, and then you can actually implement this in your lab classes. So then let me continue with this Timosenko beam theory based frame finite element. So far what we did to the detailed derivations I am actually going to give you as your home assignment, so you have to do yourselves. So now back to Timosenko beam element. So is there any other question before that? So see what we did was know this. So we had this energy functional I, which would be there in your notes. So I'll just write few terms just to remind you that what we did. So we had this 0 to L du naught. As I said, we are also considering the axial displacement here, d theta z by dx transpose. This I had actually done, EA 0 and EIZZ, and then you had this du naught by dx and d theta z by dx. So this was one energy term which includes the strain energy due to stretching of the centroidal axis and bending of the centroidal axis. That is these two energy terms are including incorporating that, plus half of transverse shear energy that we have written separately, and that was GA into minus theta z plus dV by dx transpose into minus theta z plus dV by dx. This is there in your notes, dx. So this is transverse shear strain energy, second term, and then we had potential of distributed external forces, which was integral 0 to L. We have written that as u naught v theta z transpose, and then the forces qx qy 0 and dx, and then minus you have the internal force contribution, so that we have written in terms of degrees of freedom u naught v1 theta z1. This is there actually in your notes, so I am just summarizing what we did last time. And the forces are here, say minus q1, minus s1, minus m1, q2, s2 and m2. So this is what you had got, and based on this we discussed actually interpolation. So interpolation of can someone switch up this slide, actually it reflects. So interpolation of u naught v and theta z. So we discussed by looking at of course this integral functional, Hash derivative of u is u first, similarly Hash derivative of theta z is first derivative, Hash derivative of v is first So what we need is, and so I talked to you about this interpolation. We need u naught v theta z as degrees of freedom at the end nodes being primary variables to make sure that the deformed configuration of the structure is actually a continuous domain when we assemble all the deformed elements together. So for that we need know the u, v and theta z as the degrees of freedom at the end nodes of the element. So that is what at the beginning also I talked about what are the degrees of freedom, and then based on this we said that we must assume at least a linear polynomial for u, for v as well as for theta z, and therefore we ended up saying that we express unknown constant in terms of values of the variables at node points. So this was n naught n1 into u naught 1 plus n2 into u naught 2. Similarly v we said n1 into v1 plus n2 into v2, and theta z is n1 into theta z1 plus n2 into theta z2. So the same kind of interpolation where n1 is 1 minus x by L and n2 was x by L. This we had derived earlier, so the same shape functions. And now for substituting this finally into the this integral functional, and then by taking delta I equal to 0, you will derive the element level governing equation. So this you can put in the matrix vector form. So same thing, if you want, you can write as u naught v theta z is equal to this whole displacement and rotation vector put together can be written in terms of shape functions matrix, so that is interpolation matrix, and vector of elemental degrees of freedom, that is u naught 1 v1 theta z1 u naught 2 v2 and theta z2. So as we know, n1 is u naught is n1 u naught 1 plus n2 into u naught 2. So the first equation is going to give you that. So therefore you need to put here n1 0 0, then n2 here, and again 0 0, so that when I multiply the first row with the this vector here, this vector, you get same thing, that u naught is n1 u naught 1 plus n2 into u naught 2. That is what you have here. Then for v you have, because we are keeping v as the second nodal variable, so first node second degree of freedom, second node also has a second degree of freedom. So you get 0 here, n1 0 0 n2 and 0, so that when you now multiply the second row with this vector of elemental degrees of freedom, you get the same expression v as n1 v1 plus n2 v2, and so the theta z is similarly 0 0 n1 0 0 n2. And this whole matrix which we have this side, we call it as interpolation matrix H, so same notation, and this is the vector of elemental degrees of freedom. So that is, this is D and this is your H. Now you also need those strain terms which are like du naught by dx, d theta by dz, and dx and so on. So du naught by dx and the vector consisting of this d theta z by dx, which is coming in your total potential energy functional. So this can also be written in a similar fashion. This side u naught 1 v1 theta z1, you can write that as actually dE u naught 2 v2 and theta z2. So what this will be, again du naught by dx is just the derivative, so which is dn1 by dx 0 0, dn2 by dx 0 0. So if you are writing a program to calculate this, you will have to first define these matrices, and then multiplication, integration you will have to do. So this is as far as du naught by dx is concerned. This would be 0 0, dn1 by dx 0 0, dn2 by dx. So this is for the first set. In the first energy term, these two quantities are coming. So these can be interpreted like this. Let me call this as B into dE. So this is the same vector of elemental degrees of freedom. This we are defining as our B. We also have in the transverse shear strain energy, so which involves minus theta z plus dV by dx. So this can be written as, of course, a single row, and this side we always put the entire vector of elemental degrees of freedom. So you have u naught v1 theta z1, u naught 2 v2 and theta z2. Now when I write this, So what are the terms? As you see here, no u naught. So the first term is going to be 0. Then the second term here, if you look at this, the first term is going to be minus n1 into theta z1 minus n2 into theta z2 plus dn1 by dx v1 plus dn2 by dx v2. Now that you are splitting into the multiplication of this and this. So here we will have the second term dn1 by dx, and for the theta you will have minus n1, then again 0, dn2 by dx and minus n2. So see, when you multiply this with this, you will get this expression. And let us call this as, because this is coming from the transverse here, so let me denote this as Bs, and of course that's the vector of elemental degrees of freedom, and this is your Bs. Now once we define these matrices, so then you can substitute all of these in your integral functional. So finally you have your integral functional I as half of integration 0 to L. You will have D transpose B transpose into this matrix in between EA0, 0 and EIZZ. You can actually derive yourself. Just look at, we are repeating the same concept. So I will not subsequently I will not repeat in same detail all of these. Only I will define minimum things subsequently. So B and then into DE. So this is the first term dx. You are just substituting this vector du naught by dx, d theta z by dx in the first energy term. Then plus you have again half integration 0 to L, and then we had GA, and this is DE transpose, and then we have here BS transpose into BS and into DE dx. That's the second energy term. So if you look at here in your I, so now I am talking about this. So this will be minus theta z plus dV by dx transpose, which would become D transpose BS transpose. So that is what I have written. D transpose BS transpose into minus theta z dV by dx, which is BS into DE. This is DE, and then the integration over the entire length. The contribution due to the external force is integral 0 to L DE transpose, then you will have H transpose, and then you will have this Qx Qy 0, and then you have this dx, and the last term is you can write it as simply as D transpose into F internal for the element. So you know how we write that. And now see, if we take equilibrium condition, so we now bring in the equilibrium condition in terms of the psi. So basically we are saying that delta I equal to 0 for arbitrary delta D. So if you follow all the steps what we did earlier, only thing is now we have one term here, another term here, otherwise the rest of the things are same. So it's exactly the same fashion. So if you do this, finally you are going to get similar way, with whatever element level Gaussian equation we have been writing so far. So KEDE, please yourself do the intermediate steps and see that how you get to this, although is actually same exercise what we did earlier, and this plus F internal. So this is what you will get. And now if you individually look at this KE will be now coming from the two terms. So one is integral 0 to L B transpose, and then this matrix EA0 cross sectional stiffness properties EZZ into B dx, and plus the second term is integral 0 to L GA into BS transpose into BS into dx. So now your stiffness is consisting of two. This is because of axial and bending rotation, and this is because of the transverse shear, these stiffnesses. You can maybe call this as 1 and 2, or you can evaluate these matrices and then finally combine them together. These two, this matrix, all of them are going to be 6. Both. This will also be, as you see, this B is 2 by 6, so its transpose is 6 by 2. This is 2 by 2. This B is 2 by 6. So finally, first one is also a 6 by 6 matrix. Here this is BS is 1 by 6. BS transpose would be 6 by 1. So finally, this also gives you 6 by 6 matrix. You can add both these. So this is what is going to be your stiffness matrix. and assuming that let us say EA, EI, ZZ and GA are constant within the element, you should work out what is finally the stiffness matrix after all the multiplications and integrations. So this is the exercise I give you as home assignment, so please work that out. So similarly, F external is equal to basically integration 0 to L, and you have this H transpose and Qx Qy 0 dx. So this also you can work out. You know H and all the matrices are defined, you should be able to work out. So what I am going to do, so you should take say the constant values of EA, EI, ZZ, GA, Qx, Qy, evaluate all these matrices and take maybe similar problems what we did earlier using Euler-Bernoulli beam or FEM element and try to see how you will actually solve same problems using this element. Now what I am going to discuss, a typical problem of what is known as shear locking. So now this is the term you are hearing probably for the first time, that what is the shear locking. Now see what happens is, as we know, if you recall Euler-Bernoulli beam theory, I had said that this is applicable for thin beams, typically where L by H is let's say no greater than 20 of that order. So before I actually introduce this term, I will just remind you that in case of Euler-Bernoulli beam theory, what we said that it is applicable for thin beams. So if I have this as a let's say entire beam, and this is the total length of the beam, and typical cross sectional dimension is let us say height h. So Euler-Bernoulli beam theory is applicable for thin beams, and thin beams is what we are saying that something L by H is actually greater than 20, let us say. I mean, of course there will be some transition, so you will have to always look at that. And one of the main thing here is that when it deforms, we had said, so we take the centroidal axis and take a normal. In the deformed configuration we say that no, this normal remains normal to the deformed centroidal axis. That is the main assumption. And what it actually means now, since we have done the Timošenko beam theory, so what it means is that gamma xy is actually 0, because rotation of the actual normal and normal drawn to the tangent to the centroidal axis, they coincide. So theta z is equal to dv by dx, so the gamma xy is 0 for Euler-Bernoulli beam theory, that means thin beam theory. And now in the Timošenko beam theory, we are considering this as, I assume we are relaxing this condition that gamma xy can be non-zero. That means normal need not remain normal to the deformed centroidal axis, but it remains straight. Of course, that assumption is still there. So now let us say what happens if we use this Timošenko beam element for actually simulating thin beam problems. So the question here is, if we use, if there is no problem if you use for thin beams Timošenko beam finite element, and for thick beams, that is where L by H is less than 20, if you use Timošenko beam element, there is no problem. But let's say we do, although a general question could be that what would happen if I use Timošenko beam element for thin beams, or if I use Euler-Bernoulli beam element for thick beams. So if you use, let us say, let me answer the first Euler-Bernoulli beam used for solving thick beam problems. What would happen? Suppose we use Euler-Bernoulli beam finite element for solving modeling or simulating thick beam problems. What could happen? Euler-Bernoulli beam element, which is actually a applicable Euler-Bernoulli beam theory, which is applicable for thin beams. If you use it for solving thick beam problems, where the cross-sectional dimension is actually comparable, let's say maybe the length is just let's say 5 times the height of the beam, and if that kind of a beam, if you model using Euler-Bernoulli beam finite element, wherein you have taken gamma xy to be 0, that is assuming that normal remains normal to the deformed centroidal axis. So what would happen? Yes, you are actually once you say that normal remains normal to the middle surface, you are putting some constraint on the deformation of the beam. So actually your deflection would be underestimated. If you let's say this is a thick beam and I solve this problem, it has certain boundary condition, maybe let's say fixed at both the ends, and there is a distributed force. If I solve this problem using Euler-Bernoulli beam element, the total deflection, whatever, no, let's say if I try to find out maximum deflection, that maximum deflection would be under predicted. That means it is going to undergo some bending as well as the transverse shear deformation, and because of transverse shear deformation, whatever additional deflection is going to come, that is not going to be modeled if you are using Euler-Bernoulli beam theory, because Euler-Bernoulli beam theory does not account for transverse shear deformation. The simple example you can think of is, if you, let's say, can you just borrow your notebook? I can remove the pen. So see, if I just try to hold it like this, so you see so much is initially this is the straight configuration, I just leave it under its self weight, so much is the deflection. But at the same time, now I will do the reverse thing, that I will fold it this side. By doing this, what I am doing, now the deflection, what is the difference? The deflection is significantly less. What I am doing by holding here, you can do the same thing, you hold this side but put up, let's say a paper clip which holds this together, you will find that the deflection is significantly less, because what is happening, when I leave it like this, there is you would see that now this normal, which was initially normal to the middle surface, is now no longer normal to the middle surface is like this, but actual normal has gone like this. So actually, of course in this case there is a relative slipping between the papers, but this is demonstrating you the transverse shear deformation. So like this, there is a transverse shear deformation is allowed. This is of course physical experiment, I am just showing. In this case it is not allowed, that means now there is no relative slipping. Of course there is action of when you are holding the paper, all the papers together, the bending stiffness itself is higher, but what I wanted to demonstrate you that if you have a thick beam, so then the total deflection is having contribution from bending as well as the transverse shear deformation. So if you use a finite element which does not account, does not allow transverse shear deformation, then the deflection is going to be under predicted. That means whatever you will simulate from finite element using Euler-Bernoulli beam theory, that would be much less than what actually you will get. So that is what would happen if you use Euler-Bernoulli beam theory for thick beams. Now the question reverse, let us reverse that question, that what would happen if we use Timošenko beam finite element for simulating thin beam problems. So what would be the problem? Yes, so now see, let us look at that. So this is the question we are going to answer. So the question I am posing is, if Timošenko beam element is used for modeling thin beams, this is the question we are posing, what would happen? So now to answer this question, let us look at what happens. So essentially the relation is with Timošenko and thin beam is through this gamma xy. So let us re-examine this gamma xy term. So as far as our interpolation is concerned, I already told you that theta z for the element we are considering, theta z is written as n1 into theta z1 plus n2 into theta z2. This I have already told you, and interpolate similarly for v you have n1 v1 plus n2 v2, isn't it? So if you look at the expression for gamma xy, which is your transverse shear strain, this is minus theta z plus dv by dx, and this theta z is is nothing but this expression, which is minus n1 is 1 minus x by l into theta z1, n2 is x by l, so minus x by l into theta z2, plus dv by dx is going to be dn1 by dx into v1, and which is minus 1 by l, so minus 1 by l into v1 and plus 1 by l into v2. So this is what would be your gamma xy when you directly substitute the interpolation for theta z and dv by dx in this expression. And now let us collect the constant terms together and the coefficient of x together. So the out of the constant terms, if you look at one set of terms is this minus theta z1, because this is a constant, and from here of course you get plus v2 minus v1 by L. So these are the constant terms, and then the x terms are, so you have, say, let me put here plus, and this is minus minus plus, so theta z1 minus theta z2 into x by L. So this is what we have as our gamma xy within the finite limit. And now if this element, Timoshenko beam element, is used for thin beam problems, then this gamma xy should approach to 0, isn't it? This is in the Timoshenko beam finite limit, gamma xy expression is given by this within an element. And now if the beam is thin, then gamma xy would actually supposed to approach to 0, because thin beam we know, we will have, thin beam is going to have higher shear rigidity compared to bending rigidity. So the predominant deformation is going to be bending, no shear. So thin beam means then gamma xy would actually approach to 0. Now if this is approaching to 0, then what happens to these variables? If gamma xy is 0, gamma xy should be 0 throughout the element, isn't it? Over the entire element, we are talking of one particular element. So this is your local element x-axis, node 1 and node 2. If gamma xy is 0, means it should be 0 throughout the element, it's not just one location. And if this has to be 0 throughout the element, so then what you need is that the constant term should be separately 0 and the coefficient of x should also be 0, then only gamma xy would be 0 throughout the element. So gamma xy approaching to 0, now this is a modeling problem. See, the physically, whatever is the beam, if you conduct an experiment, whatever is the deflection depending on the boundary condition, it will be there, you will measure that deflection. But here what we are talking of a modeling problem, that we are using Timoshenko beam finite limit for modeling thin beam problem. And in thin beam, gamma xy would be approaching to 0 within within each element everywhere. So that means this gives rise to us these two conditions, that minus theta z1 plus b2 minus b1 by L would be approaching to 0, and the second condition would be theta z1 minus theta z2. Anyway, L is constant, so it doesn't come, but you can write this will also be approaching to 0. So these are the two conditions we get. And now what is the implication of these conditions? If you look at the second condition, this condition, ultimately this is telling you that theta z1 is equal to theta z2. That's what it is telling you. I mean, theta z1 is tending to theta z2, if the second condition. As far as the first one is there, the first one condition is telling you that theta z1, that is the rotation or the slope at first node of the element, is equal to v2 minus v1 by L. So it is just giving you the relationship between the rotation and the rate of change of deflection essentially, since the element is having linear interpolation for v, so that the slope is dv by dx is going to be this. Now the second one is actually a problem. So since this is giving you kind of equation which involves both variables, that is deflection as well as rotation. So we call this constraint. Now these are constraints. Gamma xy tending to 0 is a constraint. That means in the deformation you are putting a constraint that there should be no transverse shear deformation. So this is a constraint, but we call this as consistent constraint because it involves the contributions from both the independent interpolation for rotation, that is here theta z, and v. So we call this as consistent interpolation. Whereas the second equation, you see it involves only theta. So it is just relating the theta z. So we call it as inconsistent. Consistent meaning it involves both the variables v and theta z, which are actually in thin beam, v should dv by dx should be equal to theta z. And this equation is giving you that some way. So we call it as consistent, whereas this is only giving the condition on theta z. So we call it as not interpolation, constraint. So this is inconsistent constraint, and this is inconsistent constraint. And what is the meaning of this? This tells you once theta z1 is equal to theta z2. So what it tells you is that when you are using Timasenko beam finite element for modeling thin beam problems, within the element the rotation must be constant. Once this constraint is there, now let us look at simple problem. That we have a let us say for the timing a cantilever beam, which is actually a thin beam and subjected to some transverse force, and you are discretizing this into a number of elements. So let us say maybe 3 elements. So now you have 1, 2, 3 or 4, whatever. So this is node global node 1, 2, 3, 4, 5. This is element number 1, element number 2, element number 3, element number 4. And boundary conditions here are at this point that V1 is going to be 0 and theta Z1 will also be 0. And this is a thin beam, that means length is much larger compared to the cross-sectional dimensions. So in our modeling, gamma xy is going to approach to 0. When gamma xy is going to approach to 0, these conditions are mathematically going to be enforced. That is, this condition and this condition, they would be mathematically getting enforced in your model. And when this is enforced, so now let us look at the first element, what is going to happen. First element, first node, theta z1 is already 0 from boundary conditions. Now this constraint from thin beam condition is telling you that theta z2, that is theta z2 means the rotation at this point, must also be equal to theta z1. That means theta z2 equal to 0. And once theta z2 equal to 0, then now you go to element number 2. In the element 2 also gamma xy is approaching to 0. So then that will tell you that theta z3 in the global node here, rotation here must be equal to the rotation here, and the rotation here is already 0 because of this condition. So theta z3 is also 0. So that means this condition finally imposing the condition on the mathematical model, the finite element model, that the rotation of all the nodes are actually 0. Once the rotation is 0, so then let us see then what will this constraint do. So now once the theta z1 is 0, it is going to tell you that V2 minus V1 equal to 0, and so V2 is equal to V1. V1 is 0 because we have V1 equal to 0 at this boundary. So V2 equal to 0. So mathematically it will give, if you have h tending to L by h tending to infinity, you will get actually 0 deflection. For it doesn't matter what is the load here and what is the Young's modulus of the beam, it will give you 0 deflection. If L by h is tending to infinity, that is where exactly gamma xy would actually go to 0, and then you get a 0 deflection. So now this is the modeling problem when you are using Timasenko beam finite element with the kind of interpolation we discussed for actually solving thin beam problems. And so what it actually means is that now you can think of, similarly you can try to argue out if you have a simply supported beam, if you have a clamp beam and similar situation, and you are, that's a thin beam and you are using this Timasenko beam finite element, what would happen? What kind of effect is going to be there in your deflection prediction? So this phenomena of under prediction of deflection when you use Timasenko or shear deformable finite element for thin beam problems, so deflection gets under predicted, and the associated phenomenon we call it as shear locking. So when what I want to say that when Timasenko, or rather Timasenko means later we would generalize to shear deformable. What is the meaning of shear deformable? Means the transverse shear deformation is allowed. We are removing the constraint of normal, remaining normal to the deformed centroidal axis. So when shear deformable, in this case Timasenko beam finite element is a shear deformable finite element. So when shear deformable finite, in this case beam, of course, finite element is used for modeling thin beam problems. deflection is under predicted. This is under predicted. Again, this one correction. This phenomenon, which is modeling problem, is referred to as, I think referred, shear locking or transverse shear locking. So you might be thinking that I am using a better element, it also has shear deformation in it, but you are by using it for thin beam problem, and when you look at your deflection, you find that the deflection is actually under predicted. And as I said, no, if L by H is infinity, actually deflection should be in that case actually infinity, because no, it has hardly any thickness and hardly any stiffness. So theoretically, I mean actually the deflection should be infinity if L by H is tending to infinity. But your this finite element Timosenko beam finite element, two-noded Timosenko beam finite element will give you zero deflection because of these constraints. And so this kind of a situation we refer to as shear locking. And the similar phenomenon is when you have we talk of 2D and 3D problems where there are volumetric deformations, and there are some situations where you have deformation which is volume conserving. That means the body is deforming without any change in volume. So then the volumetric strain is zero. So the similar situation, if you don't use proper element, that can give rise to what is known as volumetric locking. And this can be many of these say elastomeric materials are their deformation is nearly incompressible. So for example, rubber Poisson's ratio is nearly 0.5, so it's an incompressible material. And if you use the standard finite element formulation for modeling rubber problem, you will find that again the deflections or the deformations would be under predicted unless and until you take care of this volumetric locking. Same way if you are working on elastoplastic deformations, so then the plastic deformation is again volume conserving, I mean nearly volume conserving process, and again one has to take special care to eliminate the volumetric locking in case of elastoplastic deformations. So now here of course we are just talking of transverse shear locking problem when we use shear deformable, that is in this case Timosenko beam finite element for modeling thin beam problems. So gamma xy approaching to 0 gives rise to constraints which are finally leading to under prediction of deflection. Now how to handle it? So next question is how to eliminate shear locking. See, if you are using packages, so packages have already they will not put element which is not performing well in different kinds of situation it is supposed to be used. So the packages, whatever elements are there, they actually take care of that. So of course you can always, if go read the theory behind the individual elements you are using in a package, that will give you the information about what kind of formulation, what kind of if there is a locking problem, then how it has been handled, if the shear locking, how it has been handled, volumetric locking, how it has been handled. So package, all the elements are well tested elements, so they are tested for all of these, the formulation takes care of these problems. So here what we are trying to do is to understand that. It is not that you should not be thinking that maybe when I am using a package, probably whether my deflection is correct or not. Of course you have to make sure that you use the right type of element, and that means whatever problem you are solving, for that whatever element you are using, that element would be based on certain assumptions, so whether those assumptions are good enough, I mean accurate enough for a given problem or not. So as long as you make sure that your results will be accurate, because within the formulation they take care of all of these. So see, now the problem is, main problem here is that we have this gamma xy which is given by this expression. It has a constant term which is having both theta z as well as v term. We have a linear term which is only having theta z, and this is what is actually causing problem. If this somehow is not there, See, in our stiffness matrix contribution or in your energy contribution, if this term is not there, the problem would be solved. Because if this term is present in your equation, then theta z1 equal to theta z2 is going to be enforced when you use this element for thin problems. So if this term is not there, the problem would be solved. And actually all the methods which work, try to eliminate this shear locking is some way try to eliminate the terms which are causing problems, that is inconsistent constraints are somehow eliminated in the formulation, so that the locking problem is actually eliminated. So to do that, there are 3 different ways we can do this. So one is, now I just said, see, the problem came because the gamma xy is minus theta z plus dv by dx. Now theta z is linear in x, dv by dx is constant because v we are also taking as linear. So there is a difference in the theta z and dv by dx. So if we interpolate the v one order higher than theta z, so say theta z is interpolated using linear polynomial and v is interpolated as a quadratic polynomial, then dv by dx will also be having constant term and a linear term. Theta z is already having constant term and a linear term. So again the resulting constant would be having both v and theta z terms, so will not be inconsistent. Constraints would not be inconsistent in that case. So that is one way. So that is known as consistent interpolation. Consistent interpolation of v and theta z. That is one. And see what I am saying here, that now you have your finite element, but now I want to interpolate theta z using linear polynomial. With the minimum requirement for both of them is linear. But now to handle this problem, for theta z we are going to take a linear polynomial, but for v we want to take a quadratic polynomial. And quadratic means you will have 3 terms, and v as a degree of freedom means you will have to introduce an intermediate node here. So now the element has to have 3 nodes, and the degrees of freedom would be, if you also include the axial displacement, the problem is not related to axial, it's only because of the v and theta, that's basically bending deformation. So let me only have that. So then you will have v1 and theta z1 rotation here, but this node will only have v2, that is v as only degree of freedom, and here we will have v3 and theta z3. So if you formulate in this case, you would be saying that theta z is say linear polynomial means a0 plus a1 into x, which is now finally you write it as n1 into theta z1 plus n2 into theta z2. n1 and n2 are same, 1 minus x by l and x by l. But v you are interpolating as say b0 plus b1x plus b2 x square, and this will be in terms of those quadratic interpolation functions we actually discussed earlier. So and that means b0, b1 and b2 you can express in terms of b1, b2 and b3. Now this is the node which is at the center of the element. So if the element length is L, so this is at a distance of L by 2. So this is L by 2 here and L by 2 here. Now if you do this, let us see gamma xy, what would happen to gamma xy. Right now I don't have, I think I didn't bring my that function n1, n2, n3 for this. So I'll talk in terms of the constants themselves. So now gamma xy, which is minus theta z plus dv by dx, will give rise to minus a0 minus a1x. Of course a0, a1 can be written in terms of theta 1 and theta 2, and this will be b1 plus 2b2 x. If you just look at in terms of these unknown constants a0, a1, b0, b1 and b2, and now if you look at, I have one term minus a0 plus b1, and the second term is I am having is 2b2 minus a1 into x. So now if you look at the interpolation of transverse shear strain gamma xy is actually consistent. Why? Because when gamma xy is approaching to 0, this constant term would be approaching to 0, but then it has contribution from both. This is the contribution from theta z, this is the contribution from reflection. This was there earlier as well when we had linear interpolation for both theta z as well as v. But now if you see this term, here the linear term in x is having contribution, this is the contribution from theta z and this is the contribution from v. So 2b2 minus a1 would be approaching to 0. So it is not putting directly any restriction on the value of theta z1 or theta z2 like that. But only thing it will be giving you is the relationship between v and theta z, that is derivative of v and essentially theta z. So in this interpolation you have gamma xy which is consistent, and the resulting thin beam constraints would be both of the constraint, that is minus a0 plus b1 equal approaching to 0, 2b2 minus a1 approaching to 0, both would be consistent. So further, if you formulate your finite element level Gaussian equations and the load vector everything using this interpolation for theta z and v, now this finite element whether you use for thin beam problems or thick beam problems, it will give you the consistent results. It will not for thin beam problems it will not under predict deflection. So this is one way of formulating the eliminating transverse shear locking. And so of course you have to do the when you look at the overall degrees of freedom, so you have one intermediate node which has only if you are including u naught, then at the end nodes you are going to have 3 nodal degrees of freedom. So 3 here, 3 here, so 3 plus 3 6 and 1 degree of freedom at the center node. So the center node will have only 1 degree of freedom, that is v. So total element will have 7 degrees of freedom, and of course then one has to derive the element level Gaussian equations and so on. So I think I stop here, I will continue tomorrow. The other two methods, so one is known as interdependent interpolation of v and theta z, and third is known as reduced integration. So most of the time, because that's the easiest way to implement eliminate this transverse shear locking. So many of the finite elements you find use of reduced integration for eliminating the transverse shear locking. So we'll discuss these two methods in the next class. If you have any questions or doubts, you can ask outside.